Okay, everybody, this is the last whiteboard video for sets. We'll be talking about two operations today, union and intersection. These are two different ways to combine sets. Let's get started. Union. It's going to combine two sets. Let's start with some examples. So let's look at the set containing just true. You might call this a singleton set by analogy to singleton lists. Now, if I take the union a cup that looks like a U, but I'm going to write my U's with that little leg so we know which one is which. So the set containing just true union the set containing just false is equal to the set true comma false, which is also known as bool. The set bool union the RPS set, which has rock, paper, scissors, well, that's equal, let's write it out, true, false, union, rock, paper, scissors. Whoops. That's just going to be equal to the set that has all of these elements in it. Okay, the empty set, union bool, is just going to be equal to bool. This poor guy, it's got nothing to add. Okay, let's look at another one. The set true, union bool, is just equal to bool. No duplicates. So union you can think of as, I'm going to combine these two sets, but I'm going to make my result be a set. Like, there'll be no duplicates. There's not supposed to be any duplicates in a set, so it's good if it's already in the other set, then we'll just get both. So we can characterize that. Well, that's a little sloppy. Terrible handwriting. A union B is the union of A and B. If X in A, then X is in A union B. If Y is in B, then Y is in A union B. And sort of similarly on the other side, if Z is in A union B, then Z is in A, or Z is in B, or both. Right? These two ideas sort of characterize what a union is. Okay, so let's look at maybe one or two more examples of how union works. So let's say evens, or let's be clear. The even numbers 0, 2, 4, union the odd numbers. Here we're just talking about naturals 1, 3, 5. Okay, that's equal to all of the naturals, right? Comes from both. The evens 0, 2, 4 union the naturals, well, that's just going to be equal to the naturals. So there's a general law here that we can give. If A is a subset of B, then A, oops, that's very sloppy, A union B is just going to be equal to B. Right? The union is combining all of the elements, but if there's any duplicates, you're stuck where you are. You don't get anything new. So if everything that's in A is already in B, the union is not going to add anything, right? A nice thing to keep in mind. Okay, great. So that's union. The next operation I want to do is intersection. Oh, well, good effort, pen. Everybody tries. Okay, let's do it. Intersection produces the elements common to two sets. So where union combines two sets by being inclusive, saying, hey, yeah, give me everybody. Come on, join in. The gang's all here. Intersection says, no, I only want to see people who are members of both clubs. Okay, so let's do some examples. The set true intersection. Okay, so this is a cap, aka upside down U. I don't know. What you want to do to remember these two operations is come up with some kind of fancy mnemonic where when you see the cap, you think of something like maybe it's a members only hat that shows that you're a member of the club, and a union U is like the cup that we fill with all the things we hold in common. Those are bad mnemonics. You come up with your own mnemonics. It's hard to remember what these are. You simply need to memorize it. There's no two ways about that. Okay, so true intersect bool, which is true comma false, is going to be equal to just the set true. Okay, let's look at more. So true rock intersect false paper rock is going to be just rock, right? It's the only thing that we have in common. Rock, rock. Okay. Bool intersect RPS is going to be the empty set. Why? They have nothing in common. Okay, so similarly, empty set intersect bool, that's going to be the empty set. In fact, this is true for any set. What elements could anybody have in common with the empty set? It's got no elements. So before we saw that union with the empty set just left you where you were. Here, intersection with the empty set says, well, now we have nothing. Okay, let's do some more complex examples. Oops. The even numbers, the even naturals, intersect with the primes is equal to just the set 2. Okay, why is that? Well, this set is the set, excuse me, not just 2. 0, 2, 4, dot, dot, dot. And this is the set 2, 3, 5, 7, 11, and so on. And the only thing they have in common is that number. 2 is the only even prime. Okay, so let's see if we can give a characterization like we saw up here. So let's summarize. A cap B is the intersection of A and B. If X in A and X in B, then X is in A intersect B. And vice versa. X is in A intersect B if X is in A and X is in B. Okay, so can we give some, let's see if we can do some of these bad boys, right? So A intersect B is always going to be a subset of A, and A intersect B is always going to be a subset of B. Why? Well, look, you can't add elements with intersection. All you could do is take them away. So you'll be no larger than where you started. Okay. Some useful identities. So I want to close with talking about one or two extra sort of like variant notations that aren't really going to come up for us but are sort of relevant. So here, we've only combined sets. How would you insert something into a set? So mathematics tends to not talk about set insertion, whereas programs talk about set insertion all the time. Sets are a really common data structure, and people put things into sets all the time. So what is set insertion? Well, A, union, and then you just union in a singleton set, inserts X into A, right? It's everything in A plus X. If X was already there, then nothing changes, right? A union that singleton set won't matter at all because union sort of saturates, right? Like if we've already got the thing in there, then it's already in there. But if it's not, then you'll get a set that has it in there. One other common notation, disjoint union. And this is really a notational convention meant to just give a hint to the reader. A union, and then you write a little plus there, B, is equal to A union B with the expectation that A intersect B is empty, i.e. A and B have no common elements. And I want to tell you about this notation just because it's the sort of thing you might see. Now, this is sort of a requirement we're placing on it, right? Like, you could write something, it would be bad, but you could write something like true union plus bool, and I would say, oh my goodness, oh no, please don't do that. But it's totally fine to write something like bool union plus rock. Now, in particular, people use this disjoint union notation to talk about set insertion. If this bit didn't make sense, please don't worry about it. It's the sort of thing you might see in your math classes. I might use it later on unthinkingly. It's just a notation I want you to have seen. It's really not a big deal. The thing to focus on here are these two operations, union and intersection, because those will be what you'll be implementing in the remainder of the day. Okay, that's all I've got for the whiteboard stuff. If you have any questions, take it to Zulip, and I will be eagerly awaiting your questions. Talk to y'all soon.